Thank you very much for the invitation to speak here. I will talk about moments of L-functions over function fields, and I will focus on the family of quadratic Dirichlet L-functions. And the reason why I'm looking at function fields is that sometimes problems which are intractable over integers can be solved over the function field setting. And usually solving a function field analog of a classical analytic number theory problem can help us check some existing conjectures in literature, or sometimes we can make new conjectures. So I first want to introduce the number field problem of computing moments in families of L-functions. The family I'm going to be interested in is the family of quadratic Dirichlet L-functions. So I'm looking at L1/2 chi d. This is the quadratic character mod d. And I'm summing over fundamental discriminants of size up to x. And I want to compute the kth moment of this. Computing moments of L-functions is a problem with a long history, which goes back to Hardy and Littlewood, who introduced the moments of the Riemann zeta function to study the Lindelof hypothesis. So since then, moments became natural objects of study. For the family that we are interested in, there are conjectures for what this kth moment should be. Actually, there are conjectures for all families of L-functions, in the sense of Katz and Sarnak, who looked at low-lying zeros of L-functions in families. And they showed that over the function field, in the function field setting, these low-lying zeros, so zeros which are close to the critical point 1/2, the low-lying zeros are governed by the laws of random matrices in certain compact groups. So then, inspired by these conjectures of Katz and Sarnak, Keating and Snaith thought of modeling these L-functions by characteristic polynomials of random matrices. And then their idea was to compute the kth moment of the characteristic polynomial in a unitary group, or in our case, this has symplectic symmetry. It's a family with symplectic symmetry, so they computed the kth moment of the characteristic polynomial over the unitary symplectic group. And then their conjecture is that the kth moment should be asymptotic to x log x to the power of k times k plus 1 over 2. And here we have a constant, which I wrote it as a product between ak, which is an arithmetic factor, is given by an Euler product, and this is pretty easy to compute. And then gk is the factor which comes from random matrix theory. As usual with families of L-functions, when we compute moments, there's a limited range of moments that we can compute. For example, for this family, we can compute the first moment. This is work of Utila in the 1980s. The second moment was also computed by Utila. So Utila got the leading order term. And there's work of Sound, who improves Utila's result. And he obtains a full polynomial of degree 3 in this case. And the third moment is also known due to Sound. The fourth moment.
You are leaving out a few other names.
Yeah, I will mention that. The fourth moment is hasn't been written down explicitly. It is believed that maybe on GRH, one can get an asymptotic formula using ideas of Sound and Young, who computed the second moment of the family of quadratic twists of a modular form. But this hasn't been written down explicitly. And as you said, there are other conjectures using a different approach, using the multiple Dirichlet series approach. This is work of Diaconu, Goldfeld, and Hofstein, who also recovered these conjectures for moments. And actually, their work allows them to predict that for cubic and higher moments, there should be lower order terms. So for the cubic moment, yeah?
Actually, prove its proofs in the case of the leading
Right, for the leading order term. So.
and secondary terms.
Yeah, so for the polynomial of degree.
Secondary
Okay, thank you.
Well, yes, explicit, theoretically. By explicit, I mean extremely unexplicit.
So
In principle.
I should say that there is yet another approach due to Conry, Farmer, Keating, Rubinstein, and Snaith, who developed the so-called recipe method to predict that the kth moment should be asymptotic to a polynomial in log x of degree k times k plus 1 over 2. So their recipe predicts that the kth moment is asymptotic to x times a polynomial in log x of degree k times k plus 1 over 2. And we can write down explicitly the coefficients of the polynomial pk. Now, before I go to the function field moment problem, I want to give some background in function fields. I will work with fq of x, the ring of polynomials with coefficients in fq. And for simplicity, I would take q to be a prime congruent to 1 mod 4. Usually, there are similarities between the function field setting and the usual integer setting. So I can think of fq of x in analogy with the integers. And under this correspondence, the monic polynomials in the function field case would correspond to positive integers in Z. Then the norm of a polynomial, which I define it to be q to the degree of the polynomial, would correspond to the absolute value of an integer. Monic irreducible polynomials correspond to primes, and so on. Usually, when in the number field case, we are summing, let's say, an arithmetic function a of n with n going up to x, and we want to evaluate this asymptotically, then the equivalent in the function field setting is summing over polynomials, monic polynomials of a given degree. So f monic of degree n, let's say. So let me denote by mn the monic polynomials of degree n. And there are exactly q to the n such polynomials. So under this analogy, x will correspond to q to the n. And I will denote by hn the monic square-free polynomials of degree n. And I can write down a formula for the cardinality of hn with no error term. So this is q to the n times 1 minus 1 over q. Now, let me define the zeta function in this setting. Just like the usual Riemann zeta function, this will be a sum over monic polynomials of 1 over the norm of f to the s. And if I group the polynomials according to the degree, then this is just a geometric series. And the zeta function is just 1 over 1 minus q to the 1 minus s. So it's very simple. And in particular, we see that we have a pole at s is equal to 1. And we have no zeros. In general, I will work with the variable u, which is q to the minus s. This is more convenient for the function field setting. So now the zeta function will become a sum over monic polynomials, u to the degree of the polynomial. And this will just be 1 over 1 minus qu. So I have a pole at 1 over q and, of course, no zeros. Now I want to define the quadratic character before I define the L function associated to it. This will just be the Legendre symbol d over f. And once I have the quadratic character, the L function is what I would expect. It's a sum of harmonic polynomials, chi d of f over the norm of f to the s. And again, with the change of variables, u is q to the minus s, L of u chi d will be the sum of chi d of f u to the degree of f. Now, if d is not a square, then just like what I did for the zeta function, I group the polynomials according to the degree, and if I use orthogonality of characters, it follows that if the degree of f is greater than or equal to the degree of d, then I don't get anything here. So actually, if d is not a square, L of u chi d is a polynomial. And in general, I will work with d, a square free polynomial of odd degree 2g plus 1. In this case, L of u chi d is a polynomial of degree exactly the degree of d minus 1. So the degree will be 2g. L of u chi d will satisfy a functional equation. So I can relate L of u chi d to L of 1 over q u chi d. And I know that it satisfies the Riemann hypothesis. So I know that the zeros of the L function lie on the circle of radius 1 over square root of q. Are there any questions so far? Okay, then I can define the function field problem. Before we were summing over fundamental discriminants of size up to x. Now we are summing over square free polynomials of degree 2g plus 1. And I want an asymptotic for the moment of L1 half chi d, the kth moment of this. So I want asymptotics as q to the 2g plus 1 goes to infinity. So of course here, unlike in the number field case, I can have two types of limits. I can either fix g, the genus, and let q go to infinity, or I can fix q and let g go to infinity. If I fix the genus, fix g, and let q go to infinity, then the problem is completely solved using equidistribution results of Katz and Sarnak. And in general, when q goes to infinity, we have tools available to us which are missing in the number field case. So we can prove several results. For example, we know that the twin prime conjecture is true. In this type of limit, we know that Chaula's conjecture is true. And there are various other results which we can prove in the q going to infinity limit. So instead, I will focus on the other type of limit, which is fixing q and letting the genus go to infinity. And this is usually the regime which is more similar to the number field case. So this is similar to the number field case. And usually the techniques are pretty similar. And in general, maybe we can prove a little bit stronger results over function fields in this limit, but not much stronger than over number fields. So if I want to compute the kth moment of L1 half chi d, when the genus goes to infinity, we have some results. So k is equal to 1. The first moment was computed by Andrade and Keating. They showed that the first moment is asymptotic to q to the 2g plus 1 times a linear polynomial in 2g plus 1. And they obtained an error of size q to the 3g over 2 times 1 plus epsilon. So if I want to make an analogy with the number field case, q to the 2g plus 1 would correspond to x. So this is like x times a polynomial, a linear polynomial in log x, and then this is an error of size x to the 3/4. Yeah?
The implied constant can depend on q?
Yes. Yeah. So I fix q, and the implied constant depends on q.
You're also leaving out the same result was proved quite a few years earlier, in about 1990.
Oh, this one?
Better error term.
For the function field setting, as far as I know, they were the first. No.
That's not true.
Okay, and this is.
That's just myself and Mike Berger.
I know that there is a result which sums over all monic polynomials, but over here I'm summing over square-free polynomials.
That sums up a square-free polynomial.
Okay, I apologize.
To read that part of the paper.
Okay, sorry. And what kind of error do you get?
Square root.
Okay.
We didn't write better than that.
So in the number field case, there is a paper of Matt Young, who also got square root error. And it is believed that the error should be much smaller than that. So if we are interested in the precise size of the error, then we can prove the following result. We can show that the first moment is asymptotic to this polynomial plus an explicit term of size q to the 2g plus 1 over 3 times another linear polynomial in 2g plus 1. And then we get an error of size q to the g over 2 times 1 plus epsilon. So with this correspondence, this would correspond to a term of size x to the 1 over 3. So it's a term of size roughly the cube root of the main term. And then the error is of size roughly x to the 1/4. Now, for the second and third moments, we can obtain an asymptotic formula with the full polynomial of degree k times k plus 1 over 2. And the error is bounded by q to the kg over 2 times 1 plus epsilon. So for the cubic moment, for example, we get an error of size q to the 3g over 2, which is the equivalent of x to the 3/4 in the number field case. And there are conjectures of Diaconu, Goldfeld, and Hofstein, which say that for the cubic moment, there is an explicit term of size x to the 3/4 in the number field case, which we can compute. So if we believe this conjecture, then the error term for the cubic moment seems to be sharp. And also for the second moment, we expect a term of size q to the g, so square root of the main term. So again, for the second moment, these asymptotic formulas seem to be sharp. Now, the fourth moment is more delicate. And over here, we cannot get the entire polynomial of degree 10. But we can get some of the leading order terms. So we can get the first 3 coefficients and an error of size roughly g to the 7. And there's work of Bucher and Diaconu, who consider the fourth moment summed over all monic polynomials, and they obtain the entire polynomial in the regime q goes to infinity.
Fixed q.
I know,
remember we had that email.
Yeah.
It's a little unclear in their paper, but it is fixed q.
Okay, so they fix q and they let g go to infinity, n goes to infinity. Okay. Then now I want to talk about the proofs. The ideas that go in the proofs. Actually, I should say before talking about the proofs that there are conjectures similar to the number field conjectures. These are due to Andrade and Keating, who use a method similar to the recipe. And they conjecture that the kth moment is asymptotic to q to the 2g plus 1 times a polynomial in 2g plus 1, of degree k times k plus 1 over 2. And I will just write the error term as little o of q to the 2g plus 1.
And all the predictions of the formula explicit?
Yes. Yeah. So actually, the way they write their conjecture is as a k-fold integral. And if we compute the residues of that k-fold integral, then we are left with this. So for big moments, it might be pretty difficult to compute, but for small moments, it's definitely pretty easy. And let me just explain briefly how they got to their conjecture. So we are looking at the kth moment of L1 half chi d. The idea is that instead of considering the kth moment of that, we can introduce small shifts, alpha 1 through alpha k. And we can write down conjectures for this and then let the alpha I go to 0. And it's easier to notice certain symmetries. So we consider this object, and instead of considering the L function, I will consider the completed L function, which has the advantage that it has a symmetric functional equation. So then I will look at the moment of the completed L function, and then I can recover the moment of L. Of course, at the end, I will let the alpha I go to 0, and I will recover the conjecture from over there. 2 remarks here. If I permute the alpha i's, then the answer should be the same. So I should have a symmetry under permutation of the alpha I. And because of the functional equation, I expect that if alpha I goes to minus alpha I, then the answer should be the same. So at the end of the day, the answer should preserve these symmetries. Now their idea is actually pretty simple, pretty intuitive. What they do is write each of these L functions as an infinite Dirichlet series. So if we do that, then we will get a sum over monic polynomials, f1 through fk, chi d of f1 through fk, over the product of the norm of fi to the half plus alpha I. So of course, this is not rigorous, and it cannot be made into a proof, but this is what we would expect. And we are summing over square-free polynomials. Now, if the product f1 through fk is not a square, then I expect a lot of cancellation, so I will just throw away all of those terms. And I will just keep the fi so that their product is a square. When the product is a square, let's say that this is equal to L squared, then if I change the order of summation over here, I'm basically just counting square-free polynomials, which are coprime to this polynomial L. So I will replace this by the expected value. And then this will become a sum over L monic. Then I have this arithmetic factor. And I have a sum over monic polynomials, f1 through fk, whose product is equal to L squared. It's easy to write down an Euler product for this, since everything is multiplicative. So this will be a product over primes, 1 plus this. And now I have to look at polynomials f1 through fk so that their product is equal to p squared. This can happen if one of them is p squared, the other are 1, or two of them are p and the rest are 1. So then this will be a sum over I less than or equal to j less than or equal to k, 1 over p to the 1 plus alpha I plus alpha j. And I will get some lower order terms, which shouldn't matter. So if I factor out the appropriate zeta factors, this is roughly the product of zeta of 1 plus alpha I plus alpha j. And we get some function given by an Euler product, which is analytic in a wider region. So this object already has the right shape, because we see that if the alpha i's go to 0, then this has a pole of order k times k plus 1 over 2. And we expect the power of log of k times k plus 1 over 2. Moreover, it preserves the symmetry when I permute the alpha i's, but it doesn't have the symmetry of alpha I going to minus alpha I. So then the Andrade and Keating conjecture, the conjecture is that the kth moment should be the easiest object which has this shape but preserves these symmetries. So all I have to do is add over all the possible sign choices. Now, of course, each of the summands has a lot of singularities, but somehow when we put everything together, there are no singularities, and we are left with the final answer. So if we let the alpha i's go to 0, we recover this conjecture. Any questions? Okay, so now I want to talk a little bit about the ideas of proof. I will start with the kth moment. In general, I will focus on the fourth, but these hold for any k. So I will start with the approximate functional equation. This allows me to write the kth power of L1 half chi d as roughly twice times the sum over polynomials of degree up to kg, chi d of f, dk of f over square root of the norm of f. And if I didn't use the approximate functional equation, since the L function is a polynomial of degree 2g, over here I would go up to 2kg. So this allows us to make the summation shorter. And I'm summing over square-free polynomials. So now I have the problem of evaluating the sum of chi d of f as I vary over square-free polynomials and f is fixed. So I want to evaluate the sum of chi d of f when d is square-free. And it turns out that in the function field setting, doing this is pretty easy. And why? If we look at the generating series of this, u to the degree of d, and I sum over square-free polynomials, then this is just a product over primes 1 plus chi p of f u to the degree of p. So this is exactly a ratio of L functions. It's L of u chi f over L of u squared chi f squared. Now, chi f is a quadratic character, so this is related to the zeta function. Now, zeta of u squared is just 1 over 1 minus qu squared, so this simplifies to 1 minus qu squared times L of u chi f. And over here, I'm left with a smaller Euler product over primes dividing f. Yeah, so I should have said that I'm taking q to be 1 mod 4, so I have reciprocity for free here. Of course, if I don't assume q is 1 mod 4, I have to be more careful. Now, L of u chi f has, if f is not a square, then this is just a polynomial, which has its coefficients sums over monic polynomials. And I can write 1 over this product as a sum over, I write c dividing f infinity, which means that the primes of c divide f, u to the 2 times the degree of c. So if I want to evaluate this sum over polynomials of degree 2g plus 1, all I have to do is look at the coefficient of u to the 2g plus 1 in here. So this will be a sum over monics, a sum over c whose primes divide f, and then a sum over monics of degree 2g plus 1 minus twice the degree of c, chi f of h. And then I have a difference over here, so I need to subtract a similar term. So I managed to express the sum over square-free polynomials in terms of sums over monics, and it's easier to deal with entire sums over monics than dealing with sums over square-free polynomials. And it's the same in the number field case when we want to express sums over square-free numbers in terms of sums, full sums over integers. But over there, of course, we need to introduce the Mobius function to detect the square-free condition. Over here, we have complete cancellation in the Mobius function. So making use of that, we reach this pretty simple formula. This is one big difference to the number field case, and it's something that allows us to obtain stronger results. Oh, thank you. So now we use this formula in the approximate functional equation, and we have to evaluate a sum over polynomials f of degree up to kg, dk of f over square root of the norm of f. Then we have the sum over c dividing f infinity, and the sum over monics of degree 2g plus 1 minus twice the degree of c. In general, since the primes of c divide f, I expect c to have pretty low degree, so this is a long sum. And then the idea is to use the Poisson summation formula in function fields to transform this pretty long sum into a shorter dual sum. So let me describe the Poisson summation formula in this context. For a Laurent series with coefficients in fq, the exponential was defined by David Hayes, and this is just e to the 2 pi I a1 over q, where a1 is the coefficient of 1 over x in the expansion of a. In general, so I took q to be a prime. If q is not a prime, then this should be the trace of a1. This is the exponential, and then we can define Gauss sums, g of v chi f. This is just what we would expect from the number field case. It's the sum over u mod f chi f of u e of uv over f. And this is multiplicative as a function of f, and we can determine it precisely on powers of primes. Then the Poisson summation formula takes the following form. Let's assume that the degree of f is n, which is even. Then I want to relate a sum of chi f of h, where now the degree of h is m. I want to relate it to a dual sum of size roughly n minus m. And the Poisson summation formula says that this is equal to q to the m divided by the norm of f times a term corresponding to v0, so g of 0 chi f. And over here I have q minus 1 times the sum over polynomials of degree less than or equal to n minus m minus 2, g of v chi f, minus a similar sum of length n minus m minus 1. So the precise form is not that important right now. What matters is that this sum has length roughly n minus m. So now if this is a long sum, the dual sum should be shorter.
It was a sum of length n, and now n is bigger than n, no? Because n is kg.
So in general,
That's what you're doing now, right?
until now I just talked about the kth moments. For the fourth moment, I'm not using Poisson summation everywhere, but I'm just sweeping that under the rug. Of course, if the degree of f, if this is small, there is no point in using Poisson summation. But I just decided to ignore this for now. So if I use Poisson summation over here, I end up with the sum over polynomials f of degree up to kg, dk of f over f. Then I have the sum over c. And over here I get the term coming from V0, g of 0 chi f, plus roughly the term of length. Now I have the degree of f minus 2g plus twice the degree of c. Roughly this. So of course I need to consider V0 and V non-zero separately. If V is 0, then this will be a main term. From my knowledge of Gauss sums, I know that g of 0 chi f is not 0 if and only if f is a square. And in this case, g of 0 chi f is just phi of f. So this should be pretty simple to evaluate. If I write f as L squared, then this will be a sum over polynomials L of degree up to kg over 2 now, dk of L squared over L, and the sum over C and the Euler phi function will introduce some small Euler product over primes dividing L. So of course, using standard techniques, we can use contour integration and write this as an integral. If I look at the generating series of this function, so I sum over L dk of L squared, then this is a product over primes. Now dk of p squared is exactly k times k plus 1 over 2. And I will have some lower order terms. So I can factor out a zeta function here. So this is zeta of u to the k times k plus 1 over 2 times some function ck of u, which is analytic in a wider region. So I can just express this sum as an integral. And if I shift contours and evaluate the pole at 1 over q, I will pick up the main term. So this will be q to the 2g plus 1 times a polynomial p1 in 2g plus 1 of degree k times k plus 1 over 2. And then I get some error term, which comes from bounding the integral over a new contour. In general, for moments bigger than 1, the error will be an acceptable error term. But for the first moment, I'm actually interested in the size of the error term. And it turns out that the error is of size q to the g. So for k is equal to 1, I get q to the 2g plus 1 times a polynomial in 2g plus 1, linear polynomial, plus an error term, which is of size q to the g. And the error is given in an integral form. Now, the integral has a natural boundary, so there is no way I can compute this integral, and I cannot shift contours more. So I will just leave the error term in that explicit integral form. And it will turn out that this error actually cancels out with some other terms that we consider. So now I need to consider v non-zero. When v is non-zero, since the Gauss sum is multiplicative as a function of f, if I look at the generating function of this, w to the degree of f, then this is roughly L of w chi v, and I have a divisor function here, L of w chi v to the k, times some Euler product, which I'm ignoring for now. So if V is a square, then I have a pole when W is equal to 1 over Q. So I should consider V square and V non-square separately. So if V is a square, then for the third and fourth moments, I will actually get that V square contributes another term of size as big as the V0 term. So this is some polynomial P2 into G plus 1, again of degree k times k plus 1 over 2. For the second moment, I get a term of size q to the 2g plus 1 times g. So we get a smaller power than what V0 contributes. And when k is equal to 1, then this is the more interesting case. We don't get something as big as the main term, but it will turn out that V square in this case contributes exactly a term of size q to the g, which cancels out with this error, and a term of size q to the 2g plus 1 over 3. So let me just give a heuristic explanation for why we expect to get something like this. Okay, so let me go back here. I'm summing over polynomials of degree roughly the degree of f minus 2g plus twice the degree of c. So I will write it over here. Then I need, of course, I need this to be positive. On the other hand, I'm summing over polynomial c whose primes divide f. So in general, I can think of c having degree less than the degree of f. So if the degree of c is less than the degree of f, and I combine these two conditions, this would give that the degree of f must be bigger than 2g over 3. And for the first moment, I'm summing over polynomials of degree up to g. On the other hand, in the Poisson summation formula over here, I actually lied a little bit. Here I have a difference. And I'm taking v square, and on average, g of L squared chi f over square root of the norm of f is roughly 1. So if I pretend that this is equal to exactly 1, and I plug it in over here, well, over here, but keep in mind that we have a difference, then that difference will be actually equal to exactly minus 1. So it's a constant term. So if we plug that over there, we will roughly get that v square in this case is just the sum over polynomials of degree between 2g over 3 and g, and we are summing 1. So this, of course, contributes a term of size q to the 2g over 3 and a term of size q to the g. So if we do everything rigorously, we will get exactly the term of size q to the 2g plus 1 over 3 times the polynomial, linear polynomial into g plus 1, minus the term of size q to the g, which is exactly the negative of what I had before. So these two cancel out very nicely, and we are left with this secondary order term and with the error term from the other terms. Yeah? I'm just saying heuristically. Let's assume, for example, that c is square free. Okay. Then we must have that the degree of c is less than the degree of f.
There's no reason why there are many c which are, when the power go up, you mean they don't count?
This is just a heuristic explanation, so I'm not proving anything rigorously. All I'm trying to say is that roughly, when the degree of f reaches 2g over 3, we have some kind of discontinuity, which contributes to this lower order term. So now we are left with v non-square, which in some sense is the hardest term to deal with. If v is not a square, then let me rewrite this off diagonal term in a simpler way. So this will be roughly the integral over the critical circle of radius 1 over square root of q Then I have the sum over polynomials of degree up to kg. 1 over w to the degree of f over the norm of f. And then I have the sum over v of degree roughly the same as the degree of f. So here I just use Poisson's Perron's formula, basically Cauchy. Okay, so for moments less than 4, I can quite easily bound this term. For example, I can use the Lindelof bound for these L functions. I know that the Riemann hypothesis is true in this context, so I can use Lindelof for these L functions. Or I can use more refined arguments along the lines of the work of Sound and Harper for bounding moments of the Riemann zeta function. So we can use upper bounds for moments. And if we do that, then we get that this is bounded by q to the kg over 2 times 1 plus epsilon. So of course, this is a good error term. Now if I try to do the same thing, so either use Lindelof or use upper bounds for moments for the fourth moment, then of course I get something which is as big as the main term. So we need to do something more here. And one of the key things to notice is that over here I'm integrating around a circle of radius 1 over square root of q. So this is like integrating along the line with real part equal to 1/2. So when w is close to the critical point, 1 over square root of q, I should expect this cell function to be pretty big. However, as I move along, as I move further from the critical point, this cell function should get smaller. So we should try to exploit that here. And we can prove something of this form, upper bounds. So this goes back to work of Sound and Harper. We can show that the sum over square free of degree 2g plus 1, L of w chi d to the fourth. This is bounded by q to the 2g plus 1 times g to the 4 plus epsilon times the minimum between g and 1 over theta to the 6, where theta is the argument of w. So what that is saying is that when I integrate along the circle, if I'm on a small arc around the origin of angle 1 over g, then I expect to get a power of g to the 10. So over here, I expect to get a power of g to the 10. When I'm far from the critical point, then the upper bound is g to the 4 times theta to the negative 6. Since this is a small arc, I can just use the bound of g to the 10, and I multiply by the length of the arc, which is 1 over g. So over here, I will get a bound of g to the 9. Now, if I integrate theta from minus 1 over theta to the negative 6 from minus 1 over g to 1 over g, again over here I will get a bound of size g to the 9 plus epsilon. So this allows me to get the main term, the g to the 10 term in the asymptotic formula. So this means that this off-off diagonal term is bounded by g to the 9. So I get an asymptotic formula with the g to the 10 term, so the leading term, plus the error of size g to the 9. And if I want to recover some of the other terms from the polynomials, then I have to work a little harder, and I need to use a recursive argument. So the idea is the following. Remember that I had a sum over polynomials of degree up to 4g. I will truncate this at some point 4g minus alpha, where alpha is on the scale of, let's say, 100 log g. And then I have the tail, a sum between polynomials of degree 4g minus alpha and 4g. Over here, I can obtain an asymptotic formula, just like what I did before. So this will be q to the 2g plus 1 times a polynomial in 4g minus alpha of degree 10, So of course, this will be q to the 2g plus 1 times a term g to the 10. Then I get something involving g to the 9 times alpha. I get a g to the 9 term, g to the 8 times alpha squared, and so on. From the recipe, of course, I know that these terms don't appear in the asymptotic formula, so I expect them to cancel out. And of course, they should cancel out with a contribution from the tail. So if I use Perron's formula, this will just be an integral, a contour integral of 1 minus u to the alpha over 1 minus u times u to the 4g. And now I have a shifted moment, L of u over square root of q chi d to the 4. So again, when u is close to the critical point, I can obtain an asymptotic formula if I'm not too far from the point 1 over square root of q. So just like I did before for upper bounds, I will divide this circle into two parts. A small arc around the origin, which now will have angle slightly bigger than before. So let's say angle 1 over square root of g. And I will use an asymptotic formula for this moment. I can do that. And I have an error of size g to the 9, just like before. So if I use an asymptotic formula on this small arc, I will get exactly minus b9 g to the 9 times alpha. So minus the terms involving alpha. And I get an error of size g to the 9 minus 1/2 plus epsilon. So of course, these cancel out. I have an improved error term. And on the rest of the circle, I just use upper bounds, like before. But now the upper bound will be better because this arc has length 1 over square root of g. So this will allow me to obtain an asymptotic formula with the g to the 9 term and the error of size g to the 8 plus 1/2. And I can repeat this argument a couple of times. And this will allow me to obtain the very few coefficients. So the limitation of this method is obtaining everything down to g to the 4. Because over here, when I'm far from the critical point, I get basically g to the 4. So there is nothing more that I can do. And I should say that for a long time, I thought that this off-of-diagonal term should contribute to the main term. But it turns out that it actually doesn't contribute at all. So of course, we have a contribution from v0 and a contribution from v square. And we know what the answer should be from the recipe of Andrade and Keating. So we can just take the difference of those two things. And we will see that actually v0 and v square gives everything. So v non-square doesn't contribute at all. And this is something quite special for the fourth moment, because for everything bigger than 4, this term will start to contribute to the polynomial predicted by Andrade and Keating. But I don't know how one can show that this is much smaller than g to the 4. And I don't really know why for higher moments this starts to contribute, but not for the fourth moment. OK, I will stop here. Thank you.